All right, thank you for the introduction. And I'm Raz, and I'm going to tell you about steady states of local quantum channels. This is a joint work with Itai Arad from CQT and Omer Gurevich from Technion. And let me start on quantum channels. I hope that most of you are familiar with them. They describe discrete evolution of quantum states. They are also given by in a Krauss form, usually, where the Krauss operators are this Fk. Another way to look at this is in the trajectory picture. When you take a quantum state and you apply one of the Krauss operators with some probability which corresponds to the norm of the resulting state. By repeatedly applying the channel on a state, the state of the system might converge to a steady state. The steady state is a fixed point of the quantum channel. I mean, it is fixed by it. And for the purposes of our conference, this might look as a dissipative procedure of preparing a state, a certain state, which will be the steady state, and on near-term quantum devices. And the upshot here is that this procedure leverages dissipation, which is usually the key obstacle in performing coherent unitary computation to produce a state, to prepare a state. And this is nice. So to discuss efficiency for quantum computation, we want the Krauss operators to have some notion of locality. So we assume they act on locally, for example, on nearest neighbors. And a repeated application of the channel might look as some kind of a Markov chain procedure, where in each time step, you apply one of the Krauss operators with the corresponding probability. And after some very long time, you get this pure state, which is actually sampled from the steady state distribution. So this motivates the question of what kind of steady states can we get in this type of scenario. So this type of question gains some significant attention recently, and one example is the Gibbs sampling procedure, which is basically the case where the steady state is a Gibbs state of some local Hamiltonian. This is just a quantum analog of the well-known classical Markov chain Monte Carlo, which people use on a computer to sample from some classical Gibbs state. Yeah, it is usually a procedure when you flip one of the bits and you accept the flip with some probability. It corresponds to the difference in the energies from the resulting state and the initial state. In the quantum analog of this MCMC, instead of bits, you'll need a qubit on a quantum computer, and you need quantum operations that will correspond to these Krauss operators. And however, the non-commutativity of quantum Hamiltonians keeps the recipe of choosing the right Krauss operators to give you a desired quantum Gibbs state is still elusive. It's an open question. I will not discuss this in this talk. And this is also nice because it behaves as a discrete model for thermalization that can be done on a quantum computer. Well, another example I should mention is the dissipative state engineering, which was initiated in the seminal paper by Verstraete, Wolf, and Sirac. And it is where the author basically cooked local quantum channels that yield some specific pure steady state that is interesting. For example, it is a ground state of oscillation-free Hamiltonians, it's a result of quantum computation, etc. And this is nice because it helps us understand what is the complexity these local quantum channels can encompass in a NISQI-friendly surrounding. I mean, this is a nice algorithm because it uses dissipation. That's why it gains a lot of attention. However, we know that nowadays, quantum computation is noisy. Yeah, near-term quantum devices are not perfect, and the quantum state is subjected to noise. And if you want to apply some specific channel in the quantum computer, that will actually happen on the computer will be some mixture between the desired channel, this epsilon, this E, and the noise channel. For our purpose, we assume that the noise channel the noise is one local And the noise channel is composed of one local Krauss operators. So in the picture I showed you earlier, some of the two local maps, operators will be switched to some one local noise operators. And this is the picture that we'll get. And now we ask the similar question: what kind of steady state can we get in this scenario? I mean, this is more interesting question because it's more relevant for NISC devices. So to get rigorous claims, we need to be more precise in what we want. So we want to study a few properties in our work. First, the Gibbs state. I mean, what kind of Gibbs state can we get, and do we generally get a Gibbs state as a steady state? To be more specific, if we write a steady state as a e to the minus h, I mean, take the logarithm, is h local? I mean, how local is h? And this is very intuitive. It seems intuitive because dynamics is local, but this intuition is false even classically. H might be non-local. So alternatively, we can write H as a sum, decompose it to, for example, to a Pauli decomposition, and write it as a sum of one local Hamiltonian, two local Hamiltonian, etc., and ask how does the norm of these terms behave with the increasing locality. This is a well-defined question. Another question is, what is the complexity of the steady state? Per se, what is the complexity of computing expectation values of local observables? And finally, we can ask how correlation functions in the steady state behave. These are questions that are related to the complexity of the steady state. So I will now tell you how we approach this problem. We use a perturbative analysis approach, which employs this intuition. If we start from a completely noisy scenario, where there's only noise and no two local operators, then no correlations between the qubits will be presented, and the corresponding steady state density matrix will be a product state, which is not correlated. This way, it's easy to see that the matrix logarithm, the Gibbs Hamiltonian, will be one local, non-interacting system, and therefore the Gibbs state is one local. The complexity is in P because computing marginals is easy, and there are no correlations. So this is the easy case. The hard case is no noise at all. Here, correlations might be presented because of overlapping Krauss operators. So the steady state is correlated. It can be very correlated. And I mentioned earlier that the Gibbs state might be non-local, even classically. And the complexity is as hard as the complexity of frustration-free ground state, which is basically QMA1 or BQP. So this is a very complex scenario. And what we do is we perturb between we start from the only noise case, and we slowly increase interactions, and we study this perturbatively, the steady state. Basically, this means that with some small parameter epsilon, with some probability epsilon, at each step, you choose a two local operator, and with probability 1 minus epsilon, you choose a one local operator. And we get that H is quasi-local, etc. Okay, let me cover the settings of the problem. I mean, what is the rules of the game? We study qubits sitting on connected graphs, and the channels we study are like a complex combination of edge channels on the edges. It's basically the procedure when you choose an edge randomly and apply some operator on it. Now, as I said earlier, these edge channels will be composed of a mixture of this one local dissipation on the nodes and two local channel, which is in the interaction, which is this convex mixture, which describes the case I showed you earlier. So this is the channels that we study, and just let me mention that these channels are completely general. We don't have any assumption of them, except from one assumption, that the single particle noise channels are ergodic, which means that they have unique steady state and no other modulus 1 eigenvalues. This is a very reasonable assumption to make on a wild noise that we can control, which has no symmetry. So under this assumption, we can show that this channel with some epsilon, which is smaller than 1, on finite graph, has steady state that is unique and full rank, and it's analytic in epsilon, and therefore you can expand H as a power series in epsilon, and we see that each term corresponds to some local Hamiltonian. The locality increases moderately. For example, the zero term, which corresponds in a non-interacting case, is a 1 local Hamiltonian. The first term is a 2 local Hamiltonian, etc. So this is very nice. In order to get quasi-locality, we want to get some control on the norm of this H. We need some exponential bound on it, but we couldn't get it in this work. If we will get it, we will have some radius of convergence for which this is a quasi-local, exponentially local Hamiltonian. So we got some parallel arguments, but this is the case. Let me give you some, let's say some couple of words on the proof, because it's very, very nice and simple. We introduce some very nice technique where you move from a single parameter perturbation theory into a multi-parameter perturbation theory. For each edge, you just assign different variable. This way, the problem gains some more complexity because you have a lot of parameters, but it helps you differentiate between channels coming from different areas in the lattice. And this is a very nice technique that might be used for other purposes. Here the steady state is multivariable, it's unique and full rank because of ergodicity, and it's analytic because of finiteness of the Hilbert space, because it's a solution of a linear system of equation. And the technique here, the key idea is to expand H in some multivariate expansion and show that the expansion operators are supported on the corresponding edges of the epsilon. I mean, for example, the term which corresponds to epsilon 1 is supported on the first edge. Term to correspond to epsilon 1, epsilon 2 is supported on the first and second edge, etc. And moreover, we show that this kind of disconnected term fail to appear in the expansion. And the reason is that you can actually, to get this term, you can set all the other irrelevant epsilon to 0, then disconnect the corresponding steady state, and get some product state on the between the first edge and the third edge, and therefore taking the log will take this product into a sum. I mean there won't be correlation between the edges. So that's why that's how we get the result, and this is a nice technique. Now let me mention the second result and third. Second result is on the complexity of the steady states. Suppose we have a local observable, for example, magnetization on a site. So we want to study the expectation value in the steady state. Steady state is epsilon dependent. We can expand it as a power series in epsilon, and we can move this expansion in the trace to A. I mean, do it in the Heisenberg picture, which gives us a sequence of A's, each of which correspond to some order in perturbation theory. And we can show that these terms grow moderately. They are bounded in the corresponding ball around A. And that's the result. All we need to assume on the channel is that we assume some kind of replacement noise, which is ergodic. This is only for cosmetic reasoning. I mean, you can generalize it if you like. And we show that these A's are supported in the K. The AK is supported in the K ball, and it is moreover bounded by some exponential in K, and therefore at some epsilon which is smaller than e to the 6th, this series is converges exponentially fast. It can be truncated at some point. The whole thing can be computed in some large ball around A, and with some controlled error. And this allows us to say that under this threshold, we get a 1D polynomial algorithm for computing expectation value in in 1D, we get polynomial algorithm, and in higher dimensional lattices, we get quasi-polynomial algorithms. So this bounds the complexity under this threshold. Third result is correlations. Using the assumption of the previous theorem, which is basically epsilon under this threshold, and choosing this corresponding replacement noise, then we can show that correlations function between distant observable decay exponentially with the distance, with the penalty of, with annoying prefactor, which is exponential in the size of the supports. And this is done using the two previous theorems, which is basically moving to the multivariable setup, and noting that only terms that connect A to B survive in the expansion. And these terms are long as they are large, because they are large as the distance between A to B, and they are suppressed due to this previous theorem. That's it. These are some future research questions you can ask me about, and that's for example, you can have non-unital noise. For example, replacement channel, the one from earlier. This one, the fixed point is only this state W, for example. It can be reset, for example.
My point is how to get rid of that trivial steady state. When you say that the answer is, what's the answer?
You don't have to get, you don't have necessarily, you don't have trivial unital noise in a computer. The computer might reset your, you know, for example, if it's a quantum dot, then the 1 can be decayed to 0. So that's a reset noise. So noise is not always unital. It's unital if it's, for example, a projective measurement, like in the previous lecture. Yeah.
In this case, the identity state is the...
No. No, if it was M dagger rho M, then it was due to the completeness. We can discuss this later. Yeah.
If you can please emphasize why specifically in -6?
This is what, okay, this is a great question. This is what we got. It was some proof that used a nice technique of moving to like another basis that diagonalizes the dissipation operators, this DI. And at the end, we got e to the -6. We might get a more reasonable bound. And moreover, there is some transition in the computational complexity. You know, moving from QMA or BQP into P, you might get a phase transition in the complexity, which is maybe universal or maybe lattice dimensional. So this bound is not good. I mean, maybe future research will discover a better bound.
Is there a chance to get, like, do you know if the effect of Hamiltonian is a gap? So, like, what's the probability to get a gap?
I'm not sure.
I would assume that most of the time,
I'm not.
the spectrum will just continue.
Yeah, I'm not sure. I mean, what matters here is the Gibbs state of the Hamiltonian. I mean, the Hamiltonian is like, it is emergent. I mean, it's a good question. I don't know. It should be. It's hard to compute it, however. I mean, yeah, this Hamiltonian. It's hard to get rigorous claims on it.